Hello everyone, welcome to today's Wolfram live stream. I'll be presenting on Convex Polytopes, a Paclet that I've been working on, and I'll go ahead and get started. Um, so this is a Paclet for computing Convex Polytopes. It's in the Paclet repository, um, and I'll make this notebook available um, after the live stream, but for those watching, they can kind of follow along. And yeah, we'll get started. So I'll start off with like a platonic solid, um, the dodecahedron. So the vertices you can get using polyhedron data and use the numeric function to n to just get floating points for these things. And so those are the points. What convex polytope does is makes a data structure which takes those points and figures out which points are in faces and which points are in edges and that kind of thing. Um, so this is a wrapper around an association where it's got the dimension of the thing, the embedding dimension, and vertex coordinates. It has a full phase decomposition, and it has some extra information with normals, facet normals, and their bounds, and a decomposition of the volume into simplices. I have some procedures defined, such as phase counts. So this will spit out a complete all the points, edges, faces, etc. So the dodecahedron, for instance, has 20. The zero-dimensional faces are just vertices. There are 20 of those. So that's 20 vertices with 20 faces with 1 point each in them. The one-dimensional faces are going to be edges. So those are going to have 2 vertices each. There are 30 of them, turns out. And the two-dimensional facets are going to be, there are 12 of them. Each one has 5 vertices in them. So that's how this is read. Also, there are I included up values, so you can just tell it to spit out polygons, and it'll spit out uh, graphics primitives, so you can display it. I also added a little feature like um, you can scale the faces, so you can kind of oops, you can diminish the size of the faces, scale them down. It kind of gives a nice view into the structure. I wanted to look at
If you if you convert it to a polygon, does it and then deconstruct the mesh like using mesh primitives? Is it like the same internal structure as you have, like you showed in the input form?
Yeah, so that's a good point. So yeah, you can extract out faces of a particular um, dimension. So if you wanted all the um, whoops, all the pentagons or all the two-dimensional faces. This will give you the coordinates of them.
Can I turn them into polygons too? Like two-dimensional polygons embedded in 3D. Yeah.
Yes. So, hold on.
Yeah. Can you not do graphics 3D? This is just the actual polygons as a data structure. Right? Right? It's just like the built-in one.
So like that. Okay, well, first of all, the ordering of the vertices matters. I'm not orienting them to go around. So when it's rendered, you get these erroneous sort of things. That's a good point. So I developed this a long time ago, and I'll likely refactor all this code soon. And so you're suggesting like for the two-dimensional, when I return the faces of it, to return the Wolfram system primitives.
Basically, whatever the mesh primitives function is doing, right? If you convert your whole convex polygon to the built-in polygon and then ask for its mesh primitives, (1) or (2), then it just returns, I think, nicely oriented ones.
Yeah, I think you're
Can
right.
like
So
test it
if I
out.
said like, it's like a mesh, right?
Maybe it doesn't have to be a mesh.
Well,
That
what is
should work.
the native functionality though? So you take mesh primitives of.
Yeah. Well, try just mesh primitives without anything. So just output all of them, maybe. Yeah, like this.
Yeah. Yeah, that'd be a good thing to do. So for dimension 2, I could output polygon wrappers around the vertex sets. Do you know if so? Convex hull mesh doesn't return anything above dimension 3, but are there primitives for like higher dimensional things?
I think there is, yeah. I'm just, maybe they're not as advanced as 3D ones, but I think some of them are supported. I'm not sure.
So I added support for sphere and tube and line.
Dugan, is there a way you can visualize these faces extending beyond the vertices? So you can kind of like make them planes, and then you can see the polygon as like an intersection of all these planes. Because you can make it smaller here, but can you actually extend it outwards that they kind of like overlap in this kind of like, yeah.
Yeah, you just kind of scale the thing up. fix the plot range so it doesn't. There we go.
Okay, cool. Let me see that for a second. Hmm. Interesting.
I wanted to.
So are you so are each of those faces a separate entity in the like you can can you kind of like extract them out as like separate components, sort of like what you did earlier? Like what you did further up with what Nick was saying with these different
Yeah,
objects.
you can extract out the individual facets.
So my question is there a way, and I'm just thinking about a geometric interpretation of what happens in machine learning, where you have like a function that generates a potential one of the shapes on there. Let's say like a ReLU is kind of like a bit of an angled piecewise linear transformational like function. Would you be able to stitch those together to find like what the polytope is, or is this really primarily first you have to start with this dodecahedron, whatever it is, and then figure out what the components are that way?
Yeah, so this is like solving the problem of given a set of vertices in space, what's the thing that wraps around them all?
Okay, interesting. Okay.
Now there's a dual
Okay.
problem of saying like given a bunch of like linear planes that are meeting,
Yeah.
what region of space does that entail? So you can phrase that
Yes.
by taking the normal vectors and scaling the normal vectors inversely with the offset of the planes. Anyway, you do a dual thing.
So what's a normal vector? What is a normal vector?
So each facet has a normal vector sticking perpendicular to it.
Oh, I see. Okay.
Um,
Oh, okay. Yeah. Yeah, that makes sense. Okay.
and that information I think is yeah, each facet has a normal vector.
So if I could output the vertices that give a specific, let's say there's like an input space that is a collection of specific points in a 3D space, in a three-dimensional space. Given those points, you can construct this. You can construct any polytope with any, even if they're weird and they're not symmetrical and stuff.
Yeah. So
Okay.
let me just like throw a bunch of points into space and plot it real fast. So
What ensures that that maintains convexity?
right, so
They're just random points.
some of those points are going to be interior.
I see. So given any set of points in a 3D space, there is a construction that is the outermost convex polytope where that can entail some of the points that are inside of it. Okay.
Mhm.
That makes sense. So it's like shrink wrapping some kind of thing over the points, like it's always going to form a convex shape.
Right. Yeah, it's taking the convex hull of those points. So here you can see how there are a bunch of points in the center which are ignored. For random
But
polytopes
do
like
you have
that.
no.
What happened here? Goodness.
How fast is the algorithm that finds kind of the outer polytope? Could we do this with like 100,000 points?
Let's give it 1,000 and see what the timing is.
So you have your own algorithm, not using like convex hull mesh somehow, and then destructuring it into other then.
What's that?
Are you using the built-in convex hull mesh function, or you have something else?
I wrote something else entirely. I don't know how Convex Hull computes its data. There are in 2 dimensions wrapping. You can do gift wrapping on a if the points are in a plane. You can kind of like take a line that's exterior and just kind of like follow it around and wrap the set of points. And so there's a simpler algorithm for that. In 3 dimensions, there might be a different algorithm, but I figured out an algorithm for the general case for arbitrary dimensions.
Wow. What is the algorithm?
You go through the points iteratively, and you build up volumetrically this point, a set of simplices.
Just remind us, what is the simplest again? Simplex.
A simplex is like a triangle for 2 dimensions, or a tetrahedron for 3 dimensions, that kind of thing.
Okay.
So it's the simplest volumetric form.
Mm-hmm.
Okay.
Can you turn it into polyhedron back? No, not as a set of polygons, but an actual polyhedron object.
This one, yeah. Okay. So, for instance, recover those? Set of simplices. In this case, tetrahedrons.
Is it like a computable property, or is it essential as a data structure part to store the simplices?
Was it essential? No. Or, I mean, it's essential to the algorithm. So it
So you store it as a data structure, you don't compute it like from some other parts of your data structure, right? Or at least you don't have to.
yeah. So I mean, generally, I don't really use the simplices, except it's useful if you want to compute the volume of the polytope, because each tetrahedron is easy to compute the volume of as a basic unit, and then you build it up.
So how are you constructing each tetrahedron? Are you deciding like which points to make it out of? Does it not matter? Just any.
Yeah, so it's like however the points are given, you pick the first four that make a non-collinear volumetric thing, and then you for each new you go through the vertices one by one, and that'll add a new simplex, a new tetrahedron to the interior volume, and so you fill out the volume of the thing simplicity, and so you have this like deconstruction of the object, and then it's a separate step to combine to figure out which of these triangles, let's say, are exterior and which triangles are coplanar, so you can loop them into the same facet.
Can you just go a little bit slow for those who don't have all the geometric language? That first definition you gave of a coplane linear. Yeah, how do you decide on this one?
So you
Like, will it work if
Yeah.
you just took random 4 points and created a tetrahedron, or no?
No, because you could take like if the first four vertices are like up top on the same like plane, then they won't
Yeah,
make
yeah.
a tetrahedral volume. So it's like you start with 1 point and you go to like a vertex which is maximally away from it, and then you have a line, and then you take the next vertex that's maximally away from that line, and you'll get a triangle, and then you take one of the points that's like away from that triangle, you'll get a tetrahedron, and then from there you can each new point would, in general, you have to check, but it will in general make some new tetrahedral volume elements, and then you fill up the thing. And that procedure will also kind of automatically avoid vertices that are interior to the convex hull of the thing.
You mentioned that you can do more than 3 dimensions. Do you have a way of visualizing that?
Yeah, so let's do that. Let's make a hypercube. Equals. All right, so a hypercube has 16 vertices, 32 edges, 24 squares, and 8 cubes. And the projection to 3D, it automatically just chops off the first 3 coordinate vertices. So how about if I rotate this? I'll rotate the corner vertex to the up position. I think I have to transpose. Okay.
Can you just do the 3D slices along some axis? So
Yeah,
that you
or
can just...
can you make like a slider or something for the 4th dimension?
I can make a slider for this angle of rotation, and then I can slice it next. So let me do that.
I love seeing your programming style. You're a big postfix user.
Yeah, I love postfix.
explain that for people that need
Postfix is where you write the function to the right of the object you're feeding into it. So instead of like f of x, you say x, and then you say f. And it kind of flows because I had a thing, and then I did this to it, and then I did this to it, and you get the result.
The different style of thinking about. Yeah, you can kind of code how you think about this stuff.
Mm-hmm.
Just a natural way to compose things. It's very compositional. It's basically a right composition to the left.
Yeah, but it gets a little like ugly when you have to have multiple arguments, I think. Stuff like that.
Yeah, it only works for like one thing. This is some tricky notation, I guess. It's like you can do it as a postfix. Like I wrote my up value interpreter to kind of read into something that's to the right of the function in any case. Yeah, so there's a hypercube rotating. And
rotating in the fourth dimension by that slider. Is that how you'd say it?
That's right. So if I want to take a slice of that, say I rotated it first, and then I took the polytope of it, and then I can tell it to get a slice, and I have to supply a normal vector and a slice value. So I'll cut it at the equator along the W, the fourth direction. And I get a polytope out.
Does the normal vector even make sense in 4D? Because you basically have a 3D plane, right? And normal to it, it's not a vector anymore.
The hyperplane, right?
I'm just asking about what does the normal vector make sense in 4 dimensions? Because you have not a plane but a hyperplane.
Yeah, so you have a three-dimensional space that's cutting into this this higher dimensional object, and it's
extreme, but the difference is like, so the way to maybe think about it is that in 4 dimensions it's more like a ball, so it's like a solid object. So this is a hyperplane. It's a polygonal slice of that like solid object, so it's a dimension less.
What do you mean dimension? Okay, I'm taking slices in planes, like right in 2D you slice with lines, in 3D you slice with planes, in 4D you slice with hyperplanes, which is like a 3D stuff. 3D
you could say, but you could just say that's a polygon, right? Isn't that just a polygon?
It's not a polygon. In 3D it's a polygon, it's a plane, right? In 4D you slice not with polygon but with cube or something like that.
Yeah, but exactly, but that's so it's a line is sliced with a dot, and then a plane is sliced with a line, a polygon is sliced with the plane, and then a polytope or four-dimensional polytope is sliced with a polygon, right?
Yeah.
It's just yeah, it's just one dimension less is the definition of hyperplane.
Exactly. So, here are some slices of. Let me get a different version of this one. Actually, the ones with manipulates. I made this the other day.
So that polygon there in the bottom left of Dugan's screen right now is hollow. And that's like the fundamental difference. It's what that hollow polygon is a slice of is something more like a solid object, like a ball, if it was if it was round, for example.
Yeah.
Yeah. So here I have a hypercube, and I'm taking slices of it, three-dimensional slices of it, starting from one cubic facet of it to the one on the other side. So insofar as a hypercube is an extruded three-dimensional cube into the fourth dimension, that's what's happening here. So if I manipulate this, I think this should be good. Oh, whoops. Oh, I see. Hold on. There we go. So much the same way that slicing a cube by squares will just kind of have like the same square but translated. The hypercube has the same sort of arrangement. Now, if you rotate it first, I'm going to take this and make it manipulate. At the vertex, slicing right by the vertex gives you a tetrahedron, and then then it truncates into an octahedron, and then a tetrahedron at vertex again. So if you stack all those up, you get like a tilted hypercube. And
I guess you could maybe define a slice as a yeah, it's like if you were to have a series of polygons that would fill the entire space of that four-dimensional object, it's just one of those potential shapes that the polygon could have.
yeah, so there's a number of different ways to slice up like a cube, for instance. If you were slicing it from the vertex first position, you get a triangle on one. By the vertex, you get a triangle, and then it would truncate to a hexagon.
Mhm.
to a triangle again.
It'll be cool if you could like overlay all of that slicing into one image. So you could like see slices go with some transparency to give you so you get that feeling of like solidness of the interior of that four-dimensional object.
Did you?
There we go. Yeah, look at that. That's cool.
Oops.
That multiple slices there.
Like this progression, like these tables.
Yeah, but like overlapping onto one image. Yeah, you kind of had it there just now with that roundy shape. You had like 3 slices going through it. So I had actually another question in terms of this code.
So
Could
kind
you
of
just
like kind of like this though.
extend it? Oh, it's loading. Yeah. But like do like more of those and then give them like a little bit of transparency. So you could actually like get a feel for how solid it is.
Yeah.
That'd be pretty cool. Just thinking about 5 dimensions for a moment, because why not? If you just like added another dimension, would you be able to see what this looks like in 5 dimensions and then maybe have 2 sliders for like the 4th and the 5th dimension? Or does the code not allow for that?
Yeah, so then let's do that.
Oh, I know. Maybe make 1 slider for the number of dimensions.
I like that. Let's just take things one at a time, one dimension at a time, I guess.
The dimension of dimensionality.
Yeah, I was gonna ask if there's like limiting behavior as you scale, like increase the dimensions of something, like starting from a square or something.
We will see. Let's see if it gives an error. Just stick it in. Try.
Yeah, let me start with a 5-dimensional cube. All right. 32 vertices, 80 edges, 80 squares, 40 cubes, and 10 hypercubes. 10 4-dimensional cubes as its facets. And I wonder if this, let's see, this will work. So if I slice this along some random normal vector at the equator, I'll get like a 4-dimensional thing. And if I slice that again, in a different direction, up T. Yeah.
Why do you have 5 coordinates for the 4D slice?
It's in 5 dimensions. It's a 5-dimensional
Also, like
cube.
embedded. You keep the embedding, right?
Yeah. So you have to cut it with a different normal, and then you'll get like a codimension 2 object.
The frame rate is making it hard to track. Can you move those sliders like slightly slower? For some reason the frame rate's like a bit jumpy. Oh.
Feel like
Maybe it's like should be visualized as that extrusion tube, but 2-dimensional. Right now you extrude in 2 dimensions somehow. So you kind of
Multiple
like,
of those. Multiple of those extrusion tubes.
it would have like
overlapping.
a grid sort of thing.
Yep.
Oh yeah, you couldn't just do it in 1 dimension. Yeah, that's true. Yeah, you'd have to from the grid. Oof.
Okay.
That makes it a bit easier to understand what's going on here. Could you draw every polygon in the same shape? Oh, there we go. Yeah.
This is better.
Oh, I see. Okay.
Cool.
That's nice.
Yeah.
I was trying to think about sometimes like how to visualize in one image a 5-dimensional shape, and the only to represent that in 3 dimensions is like color. So imagine you had like a solid object representing the 4-dimensional object, and then you had like a variation of colors to represent the 5th dimension.
I like that. Separate it out. Oh, because color is 2-dimensional,
And then
essentially. Or like you can have hue and saturation.
yeah, I was thinking about like luminosity maybe for the 6th dimension. I don't know. Not luminosity, sorry, like transparency or whatever, like the what we sometimes call, I think the Z, the layer.
The value. Or the alpha.
So wait, so you're saying color is 2-dimensional? Isn't color 3-dimensional? Oh, I see. Wait a minute.
Oh, you can have like RGB to it.
Yeah,
But then
I
you
guess I
could,
see what you're saying. Is like it's limited. Yeah.
just show the chromaticity plot, but it has a 3D version too. Just open the documentation for chromaticity plot 3D.
That sounds interesting. What word are you using?
Chromaticity.
permission.
Yeah, chroma. Chroma.
Oh.
Chroma color. Like Google Chrome.
Chromaticity. Okay.
Oh, Interesting. Yeah, color space is weird and pretty cool.
Yeah.
Ah. So that has to do with the psychometrics of how your eye perceives color. These plots is my understanding.
But I guess it depends on the space, and there are many of them. Who knows?
You can get pretty creative with color spaces. The RGB construct is just like a very coarse graining of what the space of colors really is. Because it's very observer dependent. That's for sure.
So root vector polytopes are fun to look at. So these are lattices, like crystallographic lattices, and so these things will kind of tessellate space, or these have root vectors.
I need to jump off now quickly, but I just what struck me about the algorithm that you developed for constructing the polytopes out of tetrahedron. Isn't that like a major problem in computer graphics where you have a shape and you want to know what the tetrahedrons are that construct like the external face of that shape?
Mhm.
I think
Yeah,
that's like a
it's a-
major like optimization issue in graphics, like for computer games and stuff.
Right. Well, for
We should
computer
actually
games,
yeah, we should actually
it's probably solved in dimension 3, but probably not solved for arbitrary dimension.
yeah, I think it's about optimization. Just like if you're gonna render a 3D space, you want to only render the faces of the things that the person can see potentially, and not have to render any information beyond like the wall, for example. But if the wall is constructed out of 3D objects in the code, you don't want to render all of the stuff that you can't see.
Right.
Yeah, we should
So,
actually yeah. It's kind of interesting. Okay, but this is fun. I'll watch the rest of the stream online.
all right. Cheers.
Ideas? Hold on. Is your root vectors is basically finite group? How do you define it?
So like they generate a Wiles group. They generate a symmetry group of space, where you treat each vector as like you reflect across each vector, and you'll get like reflections and
Yeah.
rotations. And but generally, like this is like a crystallographic thing. So if you take vertices, if you start with like one vertex and you add like one of these root vectors, you'll get another vertex, and you can keep going like that, and then you'll get like a crystallographic set of points.
Yeah. But what do you use for groups? Are you supporting all the groups? Like this is the dihedral, right? Group.
Oh,
That's what it stands for.
the D3 root lattice. You're asking me like where I got like
Yeah.
this functionality.
Yes, kinda. And whether they support like some crazy groups.
Yeah, so I wrote this myself. Just going off of Wikipedia definitions for the root vector coordinates.
I see.
Yeah. And so it's just going case by case.
So you have like so you have like E8 and all that. Yep.
Mhm. And yeah, so if I wanted to make a set of start with the origin and then just kind of naively do this. Okay. Make these spheres. And I'll make them blue. I'll make them gray. Okay, yeah, so you start with like the origin, and then you go out and make more vertices. That's like the first layer. And then from each of those, you extend it out using the same set of vectors. And then you'll get like a crystallographic structure. So if I did this a lot, you get a point cloud with a bunch of like directions in it that are pretty cool. And then you'll start to see like a bunch of patterns in it. As you dial it around. So it's pretty fun.
So the group order is basically the dimension of root vectors. So D3 is three-dimensional root vectors.
Yeah, D3. Right? I mean, there are a couple lattices in dimension 3. Oh god. Whoops.
Too many layers.
There it is. So the B3 lattice is kind of simple. And this is the cubic lattice.
Right. You're also supposed to somehow to combine them together, right, for different crystals.
Right.
Oh.
Or I'm not sure.
Yeah, I don't know how they actually combine the vectors. Is it like just different addition of those additions?
So what's really fun is to see if this I wrote all this so I could compute quasi-crystals, which relies on all this convex geometry. And so looking at like a 6-dimensional lattice, I think I broke it. Did it go through? Oh, the kernel quit. No, this won't work. So you can take one of these polytopes, get the root vector polytope of like this is E6, and then you could figure out Coxeter planes. That is planes that exhibit symmetry in the symmetry group generated by the root vectors. And then you could take the edges and vertices of that polytope and project it onto that symmetry plane and get these types of projections out of it. And these Coxeter planes are also really good for generating quasi-crystals as a cut project, aperiodic tilings as a cut projection from the lattice.
Yeah. Cool. I never understood how those are being generated, especially like when you like Garrett Lisi describes his E8 theory. There's like a whole this kind of graph, with all these particles, right? Observed and not observed.
Mm-hmm.
I never really understood how you generate this kind of quick extra planes from the group.
Yeah, so but here are some of the quasicrystals that are generated from E6 specifically. And these are like really fun. And especially like this one.
Mm.
But basically the way you find those Coxeter elements is the following. So you have a set of root vectors. You convert each root vector into a reflection matrix. That is to say, to reinitialize everything.
Like, you know, in geometric algebra, a vector is basically a reflector. So it's just it's a all vectors generate a reflection. You just sandwich whatever geometric object you have with a vector that corresponds to a reflection. Two reflections is a rotator, right? If two vectors are parallel, then you can translate things.
Okay, weird. Still blue. I don't know why. I think it's a context.
Means just in the global context too.
Yeah, I'm
Maybe
loading like
oh,
really
yeah.
old
It's not in the
package that does this, but anyway. No, everything's blue. Well, bro. Anyway,
No.
yeah, so you have a bunch of reflection matrices, and then you use that to generate a group. That's tuples of my group with the generator. And I said, so let's check if the symmetry group for D4 has 96 elements in it. Which I don't know.
Can ask, was it a group element? I think there's a group data, something. The Wolfram language.
Oh, yeah. this. I was looking at this earlier. There is there's like a symmetry group or something. Root lattice D4. Here we go. Automorphism group order. Well, anyway, so you take the group and you say like, oh wait, that doesn't make sense. Oh, I see. Switching out 192. And half those are reflections and half those are rotations. They'll get the ones that are rotations. And oh, that seems pretty boring, but you look at the eigensystem, you get out like one of these complex vectors, take the real and imaginary component, and they'll give you a basis for a plane in space that has like this one. So if I take the D4 root vector polytope, get it
It's a
wrong.
backtick. Oh, no, it's backtick.
Oh.
And another one at the end.
Everything's still blue. Anyway, okay, let's see. Root vector polytope D4. And I want to take the edges of it. Project it to the plane. And okay, yeah, so the eigenvalue for that eigenvector is probably like pi over 3 or 2 pi over 6. And so there's a rotation in the symmetry group that has an order of like 2 pi over 3, you know, a third of a turn, and projecting it onto that subspace yields something with 6-fold symmetry.
It's basically like an exponential of these eigenvalues that tell you the angle somehow, right? The imaginary part.
Resetting the kernel. Okay. Where was that? So if I looked at E6, you get something more fun to look at. Ah, there's one. Interesting decomposition on the 4-dimensional faces of the E6 root vector polytope. 270. I'm guessing it's a cube. No. No, no, it has to be something. I don't know what those are.
Well, before you had 4 faces with 8 as a hypercube. We were looking at it.
Yeah,
I think
it's
so.
like more complicated.
And 5
I don't know
maybe some Tetrahedron kind of thing.
Like a 4-dimensional cube
Because it-
has 16 vertices, so I know that's not it.
Now it's half.
I think that must be well, let's look it up. Has 54 5-dimensional faces. The 4 faces decompose to there's 702 of them. 432 with they look like, I think they're pentatopes, and 270 111s. Whatever those are. Cool. Yeah, so I got it right. 2160 of 3 cells, and then 2160 triangles, 720 edges, and then 72 vertices.
Right.
And then
So what does 111 mean? Or is it 111?
right,
Like-
111. I don't know what that notation means.
Ecstasy. Is it the Cokexta symbol? What's it?
I don't know why that didn't. Oh. Oh, I see. No. I ran into this a lot. Like this plane is boring. Hold on. Try this one. Still the same. Well, anyway, gonna load old code and see what happens. No, this isn't gonna work. I better stop before I hurt myself.
Is this one in the repository?
This one is not.
Quasi crystals.
No. It's I think I have a different version. Let me try this one. Okay, so far so good. Okay, I computed the E6 Polytope and its dual. And there we go. So here it's picking out Coxeter planes and it's sorting them by their symmetry. Okay, so this one is working. All right. So each one of these different projection planes. So this is projecting the same 6-dimensional polytope onto a 2-dimensional plane, exhibiting some type of rotational symmetry.
The same one? Which one?
Different ones. Oh, the same polytope, but different projections. So viewing it from different angles.
Yeah, then which polytope it is?
Oh, E6. The root vector polytope for E6.
Okay.
And there are a lot of these. Most of them have six-fold rotational symmetry, and then towards the back here, there are ones with four. I thought. Maybe not. Okay, well, anyway. So if I pick one of these, or someone pick one of these, I guess. Maybe number 64 would be nice to see. Quasi-crystal generated. Or let's go with 37. So here it's generating a point set.
Nice.
And on that point set, there are going to be tiles, in this case, triangles that fill in the gaps between those vertices. And this is going through each tile type one by one and computing which vertices have that adjacent to it. And in the case in this example, there are 184 different tile types. So yeah, I don't know if it's going to be something like this or something like this, but these are cut projections out of the same E6 lattice. This one is one of my favorites. You have regions of triangular, basically you have hexagons made out of equilateral triangles. Those hexagons are arranged in a triangular grid or hex grid, and then they sort of undulate in and out of regularity, and you sort of have Pac-Man encircling like little triforces.
So that's what the triangle is doing, is basically finding these different kind of regions there, right? To color differently, or what?
What'd you ask?
You had like this computation running when it was the triangle, just like trying to figure out the shapes present in the in the tiling, right?
Yeah, yeah. So, like, for one of these, like for this triangle here in that orientation, this triangle like shows up again here and again there. So for that given tile, it computes where it shows up in the tiling.
And it's periodic one, right? So you basically only cover one period, and then you can just extrapolate.
Yeah, so this is the first 20 different tile types. That's kind of neat. Let me change the color function. Ooh. Yeah, so, you know, it has its own flavor, its own texture. And if I picked a different projection plane, then you get something that's quite different. When I made these, I wish I would have saved the embedding planes. I just printed out the image, and it's kind of the projection plane's lost to the sands of time. I have to find it again. But, as it is, I have dozens and hundreds of different projection planes.
So it took a while to compute all of them.
Yeah.
Needless to should have done some. Yeah, we could. A nice data set out of it would be nice.
Mm-hmm. These, for instance, are tilings coming out of E8. So these take quite a bit longer to compute than what we just sat through. But the symmetries are really interesting. So let's see, 1, 2, 3, 4, 5, 6, 7. 14-fold symmetry coming out of the E8 lattice. Which is kind of surprising. I wouldn't suspect the group elements to have order 7 for the 8-dimensional root vectors.
Yeah.
And yeah, these are quite a bit more complicated. This is the I think this is the 30-fold one. That is the, when you think of E8, everyone goes to the 30-fold projection. So that Coxeter element of maximal rotational symmetry for E8 has a 30-fold rotation.
That's what the exceptional simple theory of everything is using.
Right.
Maybe.
So, like, I'm not sure what all is going on of gauge symmetry physics. Right. So you have all these like gauge symmetries and some sort of, I'm not sure how it relates to oh, here are the quarks and here are the bosons and here are the fermions or whatever. Like
Yep.
these vertices correspond to electrons. But insofar as you have gauge symmetries and it's a geometric set of symmetries, the moral of the story is that the prime components. So with numbers, with integers, the prime integers are infinite in extent. There are infinitely many different prime numbers that go into factorize composite integers. For geometric symmetry groups like this, the prime components are limited to a certain series of like the D and the E lattice types, B and the C, and the cubic ones.
Yeah.
And you know, the C, the B, and the D lattices are not too complicated. The more complicated symmetry groups are limited to the E series, and the E series caps out at dimension 8. So if you have this complicated geometric structure, symmetry, it's going to be decomposed into one of these prime elements. And there are a finite number of prime elements for these geometric groups. And so it's sort of, if you're operating with geometric symmetries, then you're going to be embedded under the umbrella of one of these primitive types. And the E8 is sort of the biggest umbrella for these symmetry groups. So it seems to me that it's kind of consequential that the gauge symmetry groups that we care about are embedded somewhere within E8.
Yeah, because it's like because you can get larger anyway. You can, so chances are you can find all the actual already found symmetries in E8. Or you can find any symmetry, right? Somewhere in E8.
Yeah, or a symmetry is like comprised of like an E8 times something else.
Yep.
I want to say that the Leech lattice is a 24-dimensional lattice that's like three copies of E8 oriented somehow, or I'm not sure how it decomposes, but I don't think it's its own primal element.
Yeah. It's cool.
Yeah.
I wonder whether it's possible to understand the lattice symmetries from the geometric algebra perspectives. It's kind of, there's some research I just searched for this. It exists.
Mm-hmm.
So maybe you can geometrize it even more.
All right. I think I'm gonna close down the stream.
Yeah. Thanks, Dugan. It's very interesting.
Yeah, absolutely. Let me check. Yeah, the live stream is buffering heavily. My internet connection here is not so great up on the upload. But in any case,
Well, even though the Zoom,
Hmm?
even the Zoom streaming is also kind of laggy,
Yeah.
but it's bearable. It's bearable.
All right.